Hi everybody, reporting here from Limbo. You can see I'm in a nowhere world, living that goth lifestyle. And we're going to jump in today and talk about some multidimensional variants of binary search trees. And I find it pretty fun. It's a bit of a step down from the intensity of the red-black tree. So enjoy something a little new. So we're going to start actually by talking about new operations that we can perform on sets, and specifically how we can harness a binary search tree in order to make these two operations described here very efficient. So the first thing I'd like to note is that we've seen at this point 3 different implementations of a binary search tree, of a set. The first implementation is a binary search tree. The second is a 2-3 tree, or more generally a B tree. And then the third was a red-black tree, which was a construction that was based on the B tree. Now these search tree data structures listed here are really great from the perspective of supporting operations like insert and contains for set and also delete. And what we'll see is that we can actually expand what a set is capable of to do things that aren't just, is the thing in the set, or could you get rid of this thing? Now, one of the restrictions we have so far, which we're not going to deal with today, is that this approach requires that our data can be compared to other data with some total order. So for example, in our case, we used the comparable interface as our comparison engine. So we required that everything implemented comparable in order to be stored in a set. And in a later lecture, we'll talk about how you can store things even which cannot be compared. So to give you a sense of what a set could do that's not just contains insert or delete, let's consider the select operation. So this is an operation you could add to a set where you say, please give me the ith smallest item. So for example, if our set was 1, 4, 5, 6, 9, 11, 14, 17, 20, then select 0 would take this set and give me the smallest item. When I say select 0, I'll get a 1. If I do select 3, well, that's 0, 1, 2, 3, and I get item 6. So this is just an example of another type of set operation that we can perform. We could also add, for example, the rank operation, which is the opposite of select. So for example, if I say, what is the rank of 1, I would get back 0. This is the opposite, as I said, of select. Or if I ask for the rank of 6, well, that's 0, 1, 2, 3. And these operations might be useful in some other contexts. To give you 2 more examples, we might consider a subset operation. Like, wouldn't it be great to ask a set, what are all the values you have that are between 3 and 12, for example? And that would give me 4, 5, 6, 9, 11, and that's it. And so this operation, again, easy to imagine when it might be useful. Like, I want to get all my students who have grades between 63 and 84 on an exam or something. And lastly, I'll introduce this idea of nearest. And this is actually going to be pretty important for whenever you're working on your KD tree implementation for project 2. So if we have some notion of distance between items, we might ask ourselves, what is the nearest item? So if I say nearest 6 in the set, well, the closest thing to 6 is 6. The nearest thing to 8 is 9. And the nearest thing to 10 is 9 or 11. Either one would be fine. And this operation, you can imagine, would be really handy if, I don't know, for example, I want to find the closest intersection on a map to a specific point that a user clicks on a Google Maps type application. So nearest might be something we want to support efficiently.